and magnetic resonance. He was a professor at TU Dortmund, PhD in chemistry in chemistry at ETH, and he got several postdoctoral positions in Lawrence Berkeley, and the expeditions of Professor Alex Mines, so very famous. Also, he did postdoc. Chemist. Oh, chemist. That also seems to be a physicist to me.
Yeah. Published in physical review mostly, but physical letters, but he liked chemistry. So formally it's physical chemistry. I don't know what the difference between physical chemistry and chemical.
Okay, so now he is a guest professor at the University of Science in Hefei, China. So please welcome Professor Peter. Thank you.
Thank you. Well, it's a great pleasure to be here. We discussed finally after COVID. I'm a bit closer now. Yeah, you see, so I have both partial, one in TU Dortmund and one in Hefei. So if you who have never heard about Dortmund, I have here a map of West. And Dortmund is about in the middle of Germany. This is a view of the center. Down on the right-hand side, you see an aerial view of the university campus. This is an overview. This is the math building and center. Now, students, and in case you have never heard of TU Dortmund, maybe you have heard the name Dortmund before. That's what I wanted to hear. So that's I see it quite popular in Indonesia, and it's certainly one of the top teams in the German. Usually see the black and that means black and yellow trousers of the US. Now, this is the favorite pastime of many people in Dortmund. I must admit that. But anyway, so in last year, I spent most in Hefei at this University of Science and Technology. Hefei, it's a small town in China. In people, and it's located about here. This is Shanghai, and it's one of the top universities in the world. I think in some ranking it's, well, in most ranking it's in the top 10 of the world. Anyway, as my fields of research include magnetic resonance, laser spectroscopy, of magnetic resonance in laser spectroscopy was and more look into medical physics, which is a very useful application of magnetic resonance in particular. Now, yeah, if you want to read more, just saw the website. Now let's come to the actual topic of this presentation. I was told I'm giving just an overview without going for the specialists, we might have to do that at some other time. So about tools for people doing business, for instance, machines which helped in computation years ago. Here are some intermediate models. This one, oops, this one is maybe 1,000 years, about 100 years old, was developed by a German engineer. The main difference that here you need your hands to compute. So small motorized devices, and it's faster than this one, but the main advantage here is that it's programmable and enter a code and it will execute the further human assistance. And in a way, supercomputers were actually this typical picture used humans, most, I think, with some small computational machines to calculate the trajectories of flights and of their rockets to the moon. So that's how what the computer was. If you said a computer, you actually times. But a few years later, actually, during the program, humans were then replaced by something like, this is still from the 1940s. This was one of the first really faster computers, extremely bulky, it takes up the whole room, and to operate it. It's faster, mechanical parts to do the computation, but it uses electrons in vacuum tubes. Now, in a sense, computers then get even faster. These are includes tens of thousands of individual processors. On the other hand, computers could also get smaller, and this was the first so-called. Maybe it doesn't strike you as mini, but considered to be small because it didn't take up the whole room. This was sort of a department-level supercomputer, which many universities or some universities could afford. Now, this was so roughly when I started my PhD, and of course I didn't have one of those machines available. Anyway, they got also much smaller. In the meantime, that we have, being a smartphone, a watch, or a washing machine, each of these devices has built-in computational power, stronger than anything that we have seen before. So how could this happen? How could computers so much more efficient? The main reason probably is which says that the number of transistors that people it grows exponentially with time. Roughly, transistors on the chip would double from a few individual ones in the 1960s up to hundreds of billions today. So obviously, the more transistors you can put on a single chip, the more the system gets, and also cheaper. So that these individual transistors got smaller. You see here a picture of which was a few millimeters in size, And in the at the nanometer strength length, so the most recent generation of chips is nominally 2 nanometers, which doesn't mean that the transistors are 2 nanometers in size. Overall, the feature sizes have decreased by about 6 orders of magnitude. Orders of magnitude in linear length scale, which means 12 in areal density. So this is a relatively recent chip. Of course, we cannot see the individual transistors because in total, this is M1 Pro. The M contains 184 billion transistors. So obviously, scale. So they became controlled by the Semiconductor Industry Association. It says that Moore's law continues the pace. And this has worked so far very well. Easily predict that it will not continue forever. Which are smaller than 1 atom. I think we all agree on that.
Yeah.
There is a gray zone in between where it gets harder and harder to make them smaller. It continues for a while. Now, as I mentioned, we talk about 2025, and it's planned to go to 1 nanometer in 2027, but these are the actual feature sizes. Anyway, this is evolution. Even if we could get to in terms of making features that small, that does not mean that it will work as we expect. And one reason is that the systems will start to behave differently. We all learn in introductory physics that there is linear relation. So in that means we have with the slope given by the capacitance of the. Now, if you go to small sizes, it behaves differently. If you increase the voltage, you will actually get stepwise increase, and you know, of course, that this is because charge is quantized. And these small steps become in size of your devices. So there is a famous statement by a famous physicist, Erwin Schrödinger, work with single particles. So we don't work with single atoms, we don't work with single no more than we can raise them to the zoo. Now, well, actually, the working with single particles has happened for several decades now, actually started soon after this statement. And this is one example. We can actually manipulate single example of molecules. Measured at IBM Zurich with a scanning tunneling microscope, and they arrange molecules on the surface of a silicon wafer, and then one of the atoms you see here, we moved it with the tip over, and then they moved to the next one, and the next one, and so on. And so is a molecular scale abacus. So in some sense, this is now I don't expect that we will go back. This is a mechanical device. You have material with a mechanical tip to go for future computers. but you can also build. This is, of course, an image, artificial image, but the device actually exists. Electrodes, and there is one molecule between them, and it shows transistor action circumstances. You can go even smaller. You can go to the size of a single atom. This is an example of a switch. The switch is light between two fibers. You have an atom drops through the space between them, and what happens when the atom is space, it switches the light from one fiber to. In principle, a switch could be the computer size of a single atom. Still means if you go that way, you will be limited. You cannot go. So, what are the physical boundaries for computers and the improvements? Size, as I tried to emphasize, is one such aspect, but it's not the only one and may not even be the most important. Since I already mentioned that if you go to small size, physical systems will behave differently, and one aspect, quantum systems have wave properties, as shown STM image. In this case, we have iron atoms on a forms them in waves. So obviously, such a system does not behave as a classical system. And we have, these are two aspects now. We have size, we have the quantum, and an important aspect is energy, of course, is an important aspect. At the energy efficiency of computers or time, you see an exponential decrease. Of course, there is a significant scatter, but overall, the energy consumption went down drastically over the years. Stops at 1990. I'll show you another one later, which shows that it does continue to decrease. And if we compare roughly today with the introduction of the first transistor, we saw a decrease in the energy consumption of 18 orders of magnitude. So much more than in terms of size, and it's really an impressive achievement. To me, I have here, let's assume you build this number of switches and today's operation speed function of these early devices. So the energy, instead of 100 watts, it will be 10 to the 20 watts, right? How much is 10 to the 20 watts? Brass. Obviously, that's about 10 to the 11 gigawatt. 10 to 11 gigawatt. I don't know what grid capacity of Indonesia, but it's definitely not sufficient. Because the of the Earth with nuclear power stations. One nuclear power station produces about 1 gigawatt. So if you distribute them equally, including the oceans, distance between them would be 25 meters. Right? There would be no space left for the PC or for the operator. Anyway, a more efficient way of generating the power. And you have that power available. desperate to operate your PC, what would happen? Let's assume you do a short computation, takes 1 microsecond. 1 microsecond times 10 to the 20 watt is 10 to the 14 joules. Any 14 joules is, you can convert it into your electricity bill or convert it into TNT, chemical energy. And that is, of course, a pretty famous amount of energy, which was in the first two. I mean, I know this is ridiculous, but the point is the energy efficiency of a computer is important. I think it should be that point. So if we want to, the energy efficiency cannot be too bad. To continue building more powerful computers, this energy efficiency also has to improve. It has to. And this turns out to be a problem which is even bigger than the size problem. We still have a few years where we can conduct. The Industry Association has planned to do that. This is the bigger problem. There are a number of reasons. For instance, they have to decrease the voltage limits. And there is another issue which, this is the other plot that I told you, after 1990 continued in roughly the same way. This is a different data set, that's why I'm showing it different. So there is another issue, and this horizontal line K Boltzmann times T. So K Boltzmann, that's the Boltzmann constant times Joule temperature, or the temperature at which the that's roughly here. And that's an important line for two. One, this is the average energy of every degree of. That means molecules in the air, molecules in liquid, that's why you have Brownian. That's the average energy of an electron in a wire. And if that energy is sufficient to trigger a switch, that means the room temperature is at randomly. I mean, sometimes computers behave randomly, but and at that level, it will start to be the normal. That's the second reason is, in terms of entropy generation, we have a computer which is based on Boolean logic. And it's based on Boolean logic. Unless you have another one, let me know. If it's based on Boolean logic, because it loses information along the way. And the finite temperature corresponds to the dissipation of energy. Times Ln2, which we can forget about. So every has to generate at least that amount of if it uses Boolean logic. So, as I mentioned, this is Brownian motion, and it means that switches become unstable, and it's the minimum dissipation for Boolean logic. There is hope to overcome this. Is not applied to quantum computers. I'll explain what the difference is, but in principle, for quantum means, of course, that quantum computers so I to keep improving the energy efficiency, and there is some. This is already limiting the developments. For not many years or many decades, the speed, the clock speed of a microprocessor exponential. Roughly every 2 years, you will get a processor which was twice as fast in terms of the clock speed. It's just the numbers for the microprocessors from Intel. About the year 2005, at that, it stopped completely. Since 2005, every microprocessor range of 1 to 5 gigahertz. And it's unlikely that this will ever change. And that's not switches. You can build switches which work at 100 gigahertz, no problem. And people do. You cannot operate them at high speed for extended periods because they produce too much heat. So at that point, the microprocessors got too hot, and Intel and other companies and instead went to put different cores on the same chip. And that's why we have different types. Speed, of course, is also an issue. Basically limited by the speed of light, but this is maybe minor. So what are the actual limitations that we can face? A different question we discuss in much detail is if you really need ever more transistors. As I told you, we have now microprocessors with 100 billion transistors, but they basically do the same tasks. Processors, they do additions, multiplications, and the early processors have maybe 1,000 transistors. So if you have 1 billion times as many transistors, it doesn't mean that it's 1 billion times. So one possible answer, which I will, is that it depends on the problem. For some problems, having actually helps. For others, it's not the way to go. So what types of problems are we talking about? I would like to start with a very simple one. You have a problem from number theory, which is to find so-called like 175. Square-free part is 7. The square part is 25. Obviously, for most of us, not a very interesting problem. Likely that you did something today which is based on that problem, because this is one of algorithms that is used in public key cryptography. So your message is across the internet, like you open in a web browser with an address starting with HTTPS. Then there is some public key cryptography algorithm behind. Use either this problem or similar ones. And the reason why it uses them is that the execution this algorithm increases rapidly with the number of digits. Best known classical algorithm increases roughly like this with the size of the problem. Now, it turns out you can build the sense that the execution time scales less rapidly. I'll explain them in a moment, but here are two examples. Algorithm for factorization, that's a Gauss algorithm for directly finding the square-free part. You see they increase less rapidly here. Therefore, while the classical one is inefficient. This may not look very impressive. I mean, there's still I haven't put an actual here. These are arbitrary units, but I'll give you an example. Obviously, we know if you build faster time. So over the last 5 decades or so, computers 1,000 times faster. And if you assume they will do that, this is the difference that you get. So there is no significant difference in the sense quantum algorithms are still fast. You could be more ambitious and assume that you build a computer which is not 3 orders of 20 orders of magnitude fast. May take you a very long time for the reasons that I explained before. And it would indeed help for faster problem. There is still a significant backup. If here algorithm takes 1 second to finish, at the same classical algorithm would need roughly 14 billion years. So between efficient and inefficient is obviously quite important, particularly in the context of public key cryptography. If we have a key or an algorithm which is based on, then we can say with certainty that if we have a key with 2,000 digits, it will never be cracked with the classical computer. It's not in the lifetime of the universe, which is probably good enough for all of us. If you build a quantum computer which does it in a second, then you're in trouble. Well, no. If you build a quantum computer, somebody else is in trouble. And the big motivations for trying to build quantum computers, because some problems can be solved much more efficiently on such a device. I would like to go 1 step back and explain with quantum computers, with the quantum revolution. We know, of course, that quantum mechanics was invented, say, some 100 or ago. First was the Planck constant, obviously, was proposed by Einstein in 1905, showed that this is important for the photo effect. And then we, 1925, which was 100 years ago, Heisenberg made his proposal for formalism of quantum mechanics. And this is why we're celebrating 100 years of quantum mechanics, UNESCO in the International Year of Science, Technology and Quantum Mechanics. I don't know if there was some event here. Right. I mean, this was really an international. Every country that I know had some celebration. Anyway, we have had more than 100 years in total of quantum mechanics. Why do we have classical computers as computers? First of all, I would like to mention that classical computers are semiconductors. And of course, to understand what there is and how it works and how you can use that to build switches, you need. I don't know if anybody can explain to me what the band structure is in terms of classical mechanics. Let me know. If you can calculate conductivities, if you or any property of a solid state material, you will need. This is the very foundation of solid state physics. And understand how a computer works if we don't use quantum mechanics, but still we call them classical computers. Well, in some sense, of course, we have, because everybody does that, but the main reason is engineers who actually build the computers, they don't have to understand quantum. The physicists, solid-state physicists, they can calculate the conductivities, they can calculate thermal properties, whatever, give those tables to the engineers, like IV curves and so on. And then the engineers, and they really work actually much better than if the physicists will. So in that sense, you don't have to call computers. And that's why they can be described classically. For a long time, that also meant that information was treated as classical objects. That changed roughly in 1982, mostly by proposal of two people. One was they showed that you can use quantum systems as universal computers. He didn't show anything else, but as I mentioned, the quantum system, at least not directly to classical logic, but you can embed the classical problem somehow in the quantum system. And the same year, Richard Feynman also proposed that maybe you can use quantum systems for computers and that they may be qualitatively more powerful classical systems. But he didn't prove that. It was just an idea. I mean, Feynman is famous for having in detail. So it took almost to show that this is actually true. So in 1993, these three that quantum systems are qualitatively more powerful than classical computers. But this they proved in principle it's possible. Then done the following. The quantum Fourier transform, and Peter Shor, who showed how the quantum Fourier transform to factorize integers. And this kicked off the development. And the first devices were demonstrated in 1990 using nuclear magnetic resonance. So it took another 2 years until it reached the major press. USA Today is American tabloid newspaper. It put that on the cover story, and it has an interesting paragraph. That's why I copied it out. It says here, this device would not operate on anything. So how do you operate something without physical laws? Well, the physical law is quantum mechanics. So quantum mechanics obviously is not. So, but it shows that scientists, but the wider public, and in the money section, obviously also businesses. Anyway, in some sense, what we call now the second, or some people call the second quantum revolution. Revolution was that what happened between 1900 and 1925, maybe, or 1900 and 1950. Was the foundation of quantum mechanics. And the second quantum revolution now applies the devices which operate directly on the basis of quantum mechanics. And this is one of the major funding programs of the European Union, the quantum technologies flagship computer, but other devices as well, like quantum simulators, quantum communication, and so on. Obviously, people are interested. Now, certainly, China has a huge program. So what does that actually go one step back? When we talk about computer, we always mean now digital computers. That means information numbers. So like you have the text, like hello, which codes for the characters, and then you put them into binary digits, which can have logical values of 0 and 1. And of course, you need information cannot exist without physical representation. So typical representations are, for instance, the voltage or a capacitor, or it may be the spins on a hard disk, or this or something like that. Now, if you want to process, then you have to apply logical operations. And as I mentioned, normally we use Boolean logic, and Boolean logic is based on the NOT gate, which just and then it has gate which has 2 input bits, output bit which is 1 if both input bits are 1 and 0 otherwise, or one of the problems. I meant dissipates energy, and the reason is lose information here. This is a non-reversible operation. You can go forward, but you cannot go backward. And so you lose 1 bit, which means you generate K Boltzmann times ln2 of entropy, K Boltzmann times T in terms of heat. So that's the horizontal line, if you remember. Processing. Now, a different system, like a quantum system, or represent typically will use 2 orthogonal states, for instance, 2 eigenstates of state in an electronically excited state. They can represent 0 and 1. The main point is now that quantum mechanics is linear, and so you cannot 0 or the 1 state, but you can generate an array of these states. And that's what's called now a quantum bit or qubit. And superposition state like a Schrödinger cat. And of course, there are many. However, there is only one system which is the direct implementation. And that's a spin 1/2. Spin 1/2 is the only system which has just 2 energies. Others, as I will explain, but part of the Hilbert space of that system for computation. So once you have your qubit, you have to process the information. Let's assume you have here a set of ions and with wave functions. Operation will transform this input state into an output state. And of course, if you're in quantum mechanics, this transformation is an operator, which by definition is reversible. Every unitary the information contained in input state to generate any entropy. And that's why I told you that this horizontal line is not a problem for quantum computers. Operations, even if you use known algorithm, can generate computer that has no minimum dissipation of energy. Of course, you need some control fields to implement that unitary transformation. You cannot use Boolean logic, but you can use some Boolean gates like the NOT gate. You can also implement on qubits. It's the value of the qubit, so it will bring the system from the one state to the zero state if it's a spin 100. Now, for the 2-qubit gates, it's a bit different because it has to be reversible, meaning the same number of input qubits. So if you have 2 input qubits, you need 2 output qubits. And that means you cannot use you cannot use the AND gate or the OR gate, but you can use the so-called controlled NOT gate. What is the takes 2 input bits. It's asymmetric. It has a control qubit and the target qubit. The control qubit is never changed, so it has the same as on input. The target qubit is flipped if the in state 1. So then you flip the 0 to 1, the 1 to 0. If the control qubit is, you don't have changed target qubit. So this qubit operation, and it turns out that this, together with several simulations, you can build a universal computer. Now, how much time should I spend here?
Still have like half an hour.
That's very generous. It's a very generous country. So, to go beyond the single qubit, I mean, single qubit is not interesting for a computer. So-called architecture. How do you combine the qubit? How do you actually perform computations? There are a number of possible ways to do it, but the most common one is the so-called network model. I'll have time to discuss anymore. So the network model simulates. First of all, you have a quantum register, which is a certain array of qubits, hopefully as many as possible. At the moment, people work with up to a few hundred. Sure, they hope to have thousands or millions of these qubits. Now, the first step that you need for a computation, you have to initialize the system, meaning you have to write initial information in register. Say you want to factorize the number 15, then you write 15 into the quantum. Next step is that you have to apply your algorithm, or at least the first step of it, which is this unitary transformation that I mentioned. So you transform the input state into the first output state, and then comes the second step, and so on. Then, depending on your algorithm, you have a sequence of gate operation until the algorithm you have the final result. However, that final result is still a quantum state. And what you want is not a quantum real result in terms of numbers, for instance, or yes or no, or something like that. This quantum state into classical information, that's the so-called readout process. Now, if you want to have, you should have as many qubits as possible, so the quantum register should be large, which I don't have time to go into. But the reason why this quantum computer can be more powerful is that it allows you to do many operations. And I found an interesting movie on the internet which shows how the. So let's assume you're trying to find the shortest path through So classically, you would just try, for instance, until you are blocked. Quantum mechanical, you do it, test all the possible paths simultaneously. So instead of go left and right simultaneously. And as you can see, here, the whole maze relatively quickly. Well, speed is relative. No matter how big the maze is, or does not matter. Classically, you have as the maze gets bigger, you have more and more possibilities. For the quantum process, so eventually you will reach the goal much faster. And but the point is that this is actually happening all at the same time. So, and we call it agent. The agent goes through the maze, but it's actually which goes through the whole maze together. And when one realizations reaches the output gate, then to the shortest path. And so you can, if you measure where the right go the whole path. Okay, so that's the quantum parallelism. And you can build your computer based on some physical system. And as I mentioned, the first ones were built on the basis of nuclear spins. You have a molecule, what people used for the first experiment was it's a carbon-13 nuclear spin, it's a proton nuclear spin, so you have 2 qubits, each of the states. And together, they form a very simple quantum computer. So you have a quantum processor. Now, to build that, you use a sample tube which has the molecules inside a radio frequency. You put them in a magnetic field. This is not days. It has been replaced by other systems like individual atomic ions placed in a trap, and each of them as a qubit. Other possible way are photons. Easy to make. All you need is a laser. Very quickly, it preserves the information for a very long time. So why aren't we all using photons? That they don't like to interact with each other. And for 2 qubit gate operations, you need interaction between the qubits. Space photons don't sense their presence. So you have to force them to interact. There are a photonic quantum computer with several thousand qubits. Pretty promising. And of course, semiconductors or superconductors, and superconductors are also among the leading conductors today. I don't effects in solids, quantum dots, electrons on helium surface, molecular. I guess every possible system has been proposed as a device, and at the moment it's not clear which one is the best system. It may depend on the application, and so several universities, companies are now working on implementing systems based on one of qubits. So what I showed you, it is possible. You can build compute on the basis of individual qubits. Why are these? And they're much more computers. So why are we still using classical computers? This, my laptop here is definitely a classical computer. You have your classical computers and your washing machine. So why is that? Well, first of all, the main reason is classical computer is just as powerful as a quantum computer. Most of the algorithms for which we use them, like showing a presentation, sending an email, classical algorithms are efficient. Well, it's obvious if they were not efficient, we wouldn't use them. But if you have an efficient classical algorithm, it should be gained from using a quantum system. The second reason is it turns out quantum systems are much more fragile. And therefore, that becomes a bigger and bigger problem as you're trying to increase the size of the system. Building your quantum supercomputer on the basis of superconductors. Well, you can do that as 1,000,000 qubits. However, you will operate them in a way that they produce a useful result. You can do that very well for 10 qubits, and you can do anything above that does not produce a useful result. And as I mentioned, they're more susceptible to environmental noise of errors. What causes these errors? First, you need control fields to implement the computational based operations. In our system, you apply radio frequency classes. Now, every control field, magnetic or electromagnetic fields, has a finite precision. Like a laser has its fluctuation. So cells have finite precision, but the operations that you implement, they should have ideal, should be almost ideal. And actually have to generate gate operations which are better that used to generate them. That is a challenge, but there are some solutions to that. The second reason is we always assume an ideal qubit. So you have a two-level system and you apply unitary gate operation. However, in reality, this ideal qubit is always coupled to an environment. By the way, that maybe you've heard about that is the Microsoft qubit. Supposed to use so-called Majorana modes or Majorana qubits. In some sense, also really ideal qubits. The problem is nobody has seen them so far. To the environment, you cannot initialize them. So, coupled to the environment, but it's a necessity. So this is difficult to solve, and if you have to control the interaction to the environment, but you cannot control. So if this interacts with the so-called path, it framed out of the qubit, and it's just a qubit. To avoid those problems that you can use, I already mentioned you have to operations, and there are ways to do that, and you have correction schemes. Now, every classical computer uses zero correction schemes. Error correction schemes will not work. Two main reasons. One is classical error correction. So, for instance, we generate a parity. You cannot do that in classical and quantum systems. There's a so-called no-cloning theorem which says you cannot information contained in a classical and quantum bit. And people are working hard. It has some major impact. Also, Hilbert space is pretty common. And there are regions in Hilbert space which are less affected by the environmental noise. For instance, in terms of spins, you can have singlet state. So they don't couple to magnetic noise. Or you have in optical systems, you have which are all insensitive to electrical noise and magnetic noise. And dynamical decoupling, which remove or with the environment. To actually build a useful system, you cannot just pick your favorites, combine all of them. If you're interested in this topic, you can look it up, for instance, here. And I guess I'm minutes, so I will skip the few. So when do we expect to have some people say it's always 50 years from now. For instance, in 1995, so then that will be 45. I think that will be too fast. And the point is that even if become available, so they become powerful enough to crack public key cryptographic codes, security agencies are already preparing for that. So the NSA, for instance, stores all the data in the internet 20 years. And if they have computer available, they will go back and decode the information purely across the internet today. Governments are preparing for that now, and they are changing the algorithms so it cannot be cracked by quantum computers. And this is the I shall get on the next one. This is the time scale, and it will happen in 2035. So in 10 years from now, that these quantum computers will be powerful enough. However, that is changing rapidly every now and then. For instance, this was on the assumption that you need 20 for tracking RSA 2028 code. And if you need that, then the current development, we currently have kind of a Moore's law in quantum computing, also doubling roughly every 2 years. Extrapolate, it will happen in 2035. However, note that by using smart, for instance, you can reduce the number of qubits required. And obviously that will be a closer to us. Worst case in the sense of the security of the and over the internet. So governments are actually adapting, giving out recommendations. The organizations should start to move towards these post quantum computers and prepare for the advent of a quantum computer. All this, by the way, on that what started out as a purely academic, can we build a system which processes information? Research groups with 2 to 3 people in the meantime. Millions already who are building these computers. So this has moved from an academic environment to a real environment. So coming to, let me ask following question. I showed you so far the using classical computers. Either computers be useful, and I emphatically would say yes. And as I said, billions on the suggestion that this will happen. In some sense, they're even useful today. In particular, of my favorite topics is that we can use them for quantum simulations. What's the difference between a quantum simulator and a quantum computer? A universal quantum computer which can implement any. So if a problem has a computational solution, then the universal quantum computer can find that solution. A quantum simulator is something different. That's a purpose-built system which behaves like another. Can only solve one specific problem, and obviously that are small, so it's much easier to do that. And I'll show you one example here. This is about local. You're familiar with the problem of localism. That if you have a quantum system, the ground state of that quantum system in free space is smeared out over all the available space. So, on the other hand, most objects localized, like the microphone, localized, right? Or the water bottle doesn't. And so most objects are localized. And there is some theory of that developed by P.W. Anderson with perturbations, for instance. But this is very common to study in detail. You cannot solve it analytically, and numerical solutions are very hard to come by, but you can build a quantum simulator for that. This one was based on nuclear. Worked out with a localized objects. It's in free space, which is homogeneous, so the system evolves and it spreads out information and time goes horizontal. So you see it spreads. Now let's apply a perturbation, and we change the strength of the perturbation. This was this relatively strong perturbation. You see that the spreading slows down, it actually stops and reaches a finite space. So it's finite size. So this is a localized state. And you can analyze that in terms. And what you find that there is a transition, so-called quantum phase, between a delocalized phase and the localized phase, with some interesting border between them. So this is, in my opinion, well, not surprising, an interesting application of vectors. This is a relatively large quantum qubits obviously more than you can simulate on a classical computer. Have no individual control. We can only apply global data efficient for this specific problem and a number of other problems that quantum simulator, but you cannot use it as a universal computer. Of applications, and there are of course other algorithms which were designed for quantum systems. This one is Deutsch-Chose algorithm, but it's famous because it's very easy to implement. It's the simplest possible quantum algorithm and it shows quantum. The Grover algorithm for quantum search, but they have relatively little practical. Algorithm for factorization was the first one which had obvious practical. I already mentioned quantum simulations, and these are issues which commercial, for instance, pharmaceutical companies want to use quantum simulators to optimize the design of drugs. Obviously, drugs are quantum mechanical systems, and you can use the algorithms to improve their properties, to analyze their properties, or to design material. In general optimization, there are very efficient quantum algorithms for optimization. All fields of science, not just physics. Economics, for instance, banks are using that, and they hope to forecast the evolution of stock markets and so on. This is to machine learning. In machine learning, you have feedback algorithms, quantum systems. Now, these are all relatively special ones for some communities, but maybe not for the wider public. So what we really need to make quantum is a so-called killer application. A killer application, that's why I copied this page from Wikipedia. It was coined when in the early times of computers, and the game consoles always had the problem. So either you had, well, if you wanted to sit, you needed to have good applications. The companies tried to find a game which everybody wanted to play, like Tetris. Once you had such a game, then was to buy it, and then there was a market for these consoles, and so other companies games for it. So that's what you need for a quantum computer. And in my opinion, that might be graphics processing. Obviously, if you look at the internet or if you look at your own computer, a large fraction of the storage space is taken up by graphics, be that pictures or movies. Internet traffic is. If you have an efficient way of processing graphical information, it may be very useful. How does graphics processing work? Normally, you have some matrix in the simplest case. And if you want to process that, first of all, you okay. So the reason this is for specialized chips for that. They're called GPUs or graphical processing. And because graphics processing is very, GPUs are much more powerful than CPUs. And so if you want, first of all, you encode your image. And then, okay, this is typical graphics processing operation. You encode your, so that's the encoding step. The processing is patients and then you do the decoding. And if you have an image, say, I think you chose here 16 megapixels, you will, for black and white, you need 16 megabits to represent that information, and then you have to apply your matrix multiplication. In the worst case, would be 16 million times 16, and then you decode. Now, turns out you don't need 16 million qubits, you need 20. That's pretty efficient, right? So you can say it gets even better. If you want to process the information, if you want an example, processing the information here, you're trying to detect what. So there are some very efficient quantum, very efficient. That's an important step in better. So we want to find the border between black and white. On the class, we just compare adjacent bits. If they are different, then you have for 16 megapixel, you need 16 million operations roughly. If you take a factor of 2. In quantum system, independent of the size of the matrix. That's pretty efficient, right? So I would say, yes, we can use quantum computers even today. Simulations. Second reason, future computers, even if they use classical, will be affected by quantum effects. That's what I tried to show you in the beginning, like K Boltzmann and something like that. So, if looking at this concept, more useful classical computers. Interesting argument based on Fermat's lemma. Fermat was a semiconductor physicist, and he proposed to his boss to develop semiconductor heterostructures. What are semiconductor heterostructures? I mean, so his boss said, well, Fermat didn't listen to his boss. He was awarded Nobel. Doesn't always work like that, but the point is, semiconductor heterostructures important with tons of commercial applications. Every semiconductor laser is based on heterostructures. And so the fact that this was such a useful development doesn't mean that this boss was stupid. He was probably a pretty smart person already, but in case Fermat couldn't see them either, because the applications, if you don't have the system, then you cannot have the applications. And it will happen for quantum computers. So these are some of the applications where we use now semiconductor. And that we have to be, I just show some more examples that it's often difficult to predict the usefulness. Supposedly in 1899, the head office said all possible inventions have already been made. It's probably not true. Good statement anyway. And this is definitely true in somebody at Western Union said or again, this is a true statement by the head of the biggest systems company, said there may be a world market for about 5 computer washing machines. There is no reason why anybody would want to have, again, by somebody job had to predict the future, and he was definitely become chairman of Digital Equipment Corporation, which still make these mistakes. This is a true statement. Computers only 1.5 tons or even less, I guess. So if anybody knows this statement, probably know 640K stands for 600, which is a unit smaller than a megabyte anyway. Maximum possible value for the memory which Windows could access at some point. Possibly a few games should be enough for me. Anyway, maybe I can just show and you can read it yourself. More about satellites. Dangerous to say something will never be useful, even if it's your job. But I also like to be even more ridiculous later and consider bits written on one atom instead of pressing 10 to the 11 atoms. Such not. I hope you will find it an interest. And I think this is sort of what I tried to convey in this presentation. Thank you for your attention.
Well, thank you very much for a very entertaining talk and giving us a lot of insights. I should say that Professor Peter is actually one of the early implementers of quantum computer in NMR. That is talking about. So we have several minutes left for anybody who to questions.
Thank you, Professor Peter, for the presentation. Early stages of quantum computer was based on spin computing. The most popular anymore.
Well, it depends. And spin qubit is a very general term. The early ones were liquid state NMR. It's very easy to implement. Basically, you don't have to build anything. Just if you have an NMR spectrometer, you just have to put in a pulse sequence and you're done. So no hard. But it has a severe scaling problem. It's impossible to do something useful with more than 10 qubits. Now there are still attempts, very serious attempts to build spin-based quantum computers, but that would be on basis of solids. For instance, Australia enterprise where they've built quantum computers on the basis of donors in silicon. These are phosphorus donors. Several academic and commercial companies which try to build quantum computing and systems in diamond. So they're of the color center together with neighboring nuclear speeds. So people using semiconductor quantum, where you have also, you can use the electrons or ions in these quantum dots, or also the nuclear. So I wouldn't say spins are dead, are not developing as rapidly as some of the others, like the superconducting systems or the neutral atoms.
Any other questions from the students?
I guess that's exhausted everybody.
From the beginning. So, what is, if you can give us some, advice on go from in the context of, let's say, or you can give some what is the advice
What do you mean?
us
Indonesia.
Indonesia
This room.
to live in this room.
Well, I what your current status is and where you're, how far you are in terms of the theoretical foundation or in terms of the experimental capability. But there's definitely in all parts of quantum science, there is plenty of things to do, and it depends mostly on your personal interest. I've always been in error correction and say avoiding defects, trying to build. When one of the at the moment is to build so-called logical cube. So that's the same. And believe forever you can apply as many operations as, and it reliably gives the result, independent of the noise that you have. So you error mitigation and error correction. But I mean, say that this is the best way to go for you.
All right. Okay. Any?
So I can read it for you. The question is from working on quantum machine learning, and the question is: will the future of quantum machine learning remain centered on hybrid quantum approaches?
I'm absolutely sure, yes.
And why?
Well, first of all, I mean, every quantum is certainly a hybrid device because you always need to control the system, and we need classical electronics to process the and you use classical electronics for all the feedback systems. Everything that you can, you will be doing classical because it's easier, it's cheaper, and it's available there. But every machine learning job includes tasks of the efficient classical algorithm and where quantum algorithm can improve. There are even small quantum systems with limited capabilities can speed.
He has a follow-up question. Is there a plausible path toward fully quantum learning genuinely replace classical backpropagation, for example?
That's a very good question. I could imagine, yes, but no.
Maybe the philosophy is similar to this question.
Right, yes.
You should not say no.
Yes. No, not only that, we know that quantum systems have some additional capabilities, and probably at some point somebody will find something.
Somebody will find out. Okay, yeah, that's all.
Probably not the $1 million. It's the $1 billion question.
Okay, thank you. Yeah, that's all from the Zoom.
Thank you very much. Maybe it's not the
Maybe I have
Okay.
one question. In my impression, you make kind of some about the application, about the killer applications of quantum computing. But can you also make another bet which platforms will eventually be the champion for the quantum computing, whether trapped ion, neutral atoms, superconducting qubits, and so on?
No, I won't. And I think this is, I mean, if anybody were able, and there are certainly people out there who are better at making such predictions. If it were possible, then everybody else would stop to them. So that's one. So it's. I mean, each of the current platforms has its roadmap. Efficient quantum computer, 10 to 20. Because this is unknown territory, at any point you can, it is possible that you will hit a roadblock. And in today there are which don't have known solutions. Let's give one example. Superconducting qubits. They're very many. It's not, I mentioned, it's not a problem to make a chip with 1,000 qubits. However, they have to operate at liquid helium, actually at dilution refrigerated temperature, millikelvin. And to control them at the moment, basically people have lines for every qubit, which go from room temperature millikelvin. Can you imagine to have 10 million control 10 millikelvin? This will not work. This is a problem. The people believe this can be solved. So this scaling and parallelization, which will probably have solutions in the, by putting intermediate control procedures closer to the low temperature, which means then expanding the low temperature. So there are possible solutions, but not all of them will actually work.
All right. Time is already up. So let's thanks again for see you again in the next colloquium this month. Okay.